Hello everyone, today we have our final topic of Unit 3, which is the method of Lagrange multipliers. Now, Lagrange multipliers are really a very nice way to do optimization for multivariable functions. We tried multivariable optimization earlier, and we were actually kind of using constrained optimization there because if you remember, we had a certain amount of a certain amount of wood that we could use to make a box, and we wanted to find the maximum volume that we could make with that certain amount of wood. So we were using multivariable constrained optimization because we were trying to find a perfect volume given a constraint of how much wood we were given. So in today's video, we want to cover Lagrange multipliers, which is a bit more of a nuanced way to learn about constrained optimization. And like most optimization problems, the hard part is setting it up. The actual idea behind Lagrange multipliers is actually quite easy, as you'll see coming up. So let's discuss Lagrange multipliers today. So here's a definition for Lagrange multipliers. Define the extrema of x, y, and z with a constraint such that g of x, y, and z equals k. So that's a g of x, y, and z equals k is a constraint. So that's like restricting ourselves to a certain level curve of a function. So given that constraint, we find the values of x, y, z, and lambda such that the gradient of f is equal to lambda times the gradient of g. Now, what do I mean by this? So basically, we have a multivariable function, and there's our multivariable function, and it goes out like that, so you go that way or something, I don't know. But you have a plane, or g of x, y, and z, or g of x and y, I'm drawing this in the two variable case, you have a plane, and that restricts us to a certain level curve of our function. So what we end up getting is we get here g of x, y, and z, which could be some sort of circle or some domain. So let's say we have a circle or something, and then we have the level curve of our function. That maybe looks like this or something like that. And what we want to find is we want to find these points where our gradients, which are normal to the to both functions, are the same. So that means that a gradient of f is going to be proportional to the gradient of g, right? So what we do is then we will evaluate at each point to find the largest and smallest value. So we'd evaluate the function at this point, and then we'd evaluate the function at this point, and then we'd get our candidates for extrema, and then we just compare them. So we can also rewrite this as a vector equation, which can be a little bit easier to deal with, which we will use in our example. So let's give it a try. Let's find the extrema of z equals x squared plus 2y squared on the unit circle. So just a refresher, the equation of the unit circle is x squared plus y squared is equal to 1. So again, we're going to use our equation. These are the equations we want. The radius of our unit circle is going to be 1, so g of xy is equal to 1. And then we also want nabla f equals lambda times nabla g, obviously. So now we can take our partial derivatives. So I get the equation, the vector 2x, I differentiate this, and 2y, I differentiate this, equals lambda times 2x, differentiate that, 2y, differentiate that. And then we also have our constraint equation such that x squared plus y squared equals 1. Now to find the values of lambda, x, and y, we need to kind of guess using our equations. So if I look at this first equation, this says 2x equals lambda times 2x. Now what does this mean here? So this either means that lambda is equal to 1, in that case 2x equals 2x, or I have the case where x equals 0, and in that case I have 0 equals lambda times 0, which is equal to 0. So that is where, those are the two values that would make that equation make sense. So if I have x equals 0, I plug that in to the bottom equation, which says that 4y equals lambda times 2x, or I plug it into the circle equation, x squared plus y squared equals 1. I think it's easier if we put it into the circle equation. So if I plug in x equals 0, 0 plus y squared equals 1, thus y squared equals 1, so then y equals plus or minus 1. Okay, so we found some y values. Now we're going to also cover the case where lambda equals 1, because that's the other case that makes that equation make sense. So in that case, we can plug that into our other equation, so we get 4y equals lambda, or 1, times 2y. So 4y equals 2y. Okay, so in that case, y would need to be equal to 0 in order for that to make sense. But then we also have the case where we need to consider the circle equation to find our x value. So if we use the circle equation, if y is 0, then x is going to be plus or minus 1. So we have 4 points that we've obtained. Negative 1, 0, 1, 0, negative, or 0, negative 1, and 0, 1. So now we find all of our functional values there. F of negative 1, 0 is 1, f of 1, 0 is 1, f of 0, negative 1 is 2, and f of 0, 1 is 2. So our minimum is going to be 1, and our maximum is going to be 2. Now you can see what this looks like graphically with some level curves. Let's just try to erase this. Okay, so if I look at this here, we get level curves. So these ellipses, the ellipse here and the ellipse here, are level curves of our function. And then we also have the unit circle drawn on there. So what we've found is we've found places where the gradient is proportional to the gradient of the function, right? So we found this point here where it's proportional. We found this point here where it's proportional. Found this point here where it's proportional, or sorry, this point here where it's proportional, and that point there where it's proportional. So these are where our maxima or minima could be, because that's where it touches the level curves, right? So that's really what we've found, and then we've evaluated at each of these points. Okay, so in the next video, I want to cover this Lagrange multiplier method when we have multiple constraints. So we'll cover that in the next video. We'll see you then.